Okay, so just to do a quick recap of what we've seen so far, we defined three quantities: the entropy, and as a consequence, we also defined the joint entropy and the conditional entropy. Yeah, which one? Yes. So, okay, I'll come to that maybe when I'm talking about the rest. So we've defined so far we've defined the entropy, the joint entropy between two random variables, the conditional entropy of one random variable given another, and in general these quantify the amount of randomness or uncertainty in a particular random variable or in one random variable given another. And we saw that the entropy in particular quantifies the optimal rate of compression. We looked at lossless variable length compression, where we want to design an encoder decoder pair for which the output, the expected length of the encoded version is as small as possible. At the same time, the decoder outputs exactly what is there at the source, right? No error allowed at all. And for this, we analyze the optimal compression scheme, and we show that the expected length the expected length is less than or equal to the entropy of xn, and it is lower bounded by the entropy of xn minus log E times 1 plus entropy of xn. Right? So in other words, if we look at this asymptotically, in particular if we look at what is called a memoryless source, where xi's are all independent and identically distributed, where xn is IID px, the lower and upper bounds essentially translate to expected length of the encoding of xn is less than or equal to n times the entropy of x1, which is n times the entropy corresponding to px. Because they're independent and identically distributed, the chain rule says that h of xn is summation h of xi, and each h of xi is equal to h of x. And correspondingly, it's also lower bounded by n times h of x minus log E times 1 plus n times h of x. All right. So this basically means that the entropy or the expected length is less than or equal to n times h of x, and it's greater than or equal to n times h of x minus log some constant. This is of the order of log n. Right. So the natural question is to ask what is the optimal rate. So we have an upper bound and we also have a lower bound. So which of these is tight? Is it true that the upper bound is tight, or is it true that the lower bound is tight? And so in other words, if I let n to tend to infinity, then we know exactly what is. If I look at the rate, this is less than or equal to h of x and it's greater than or equal to h of x minus order log n by n, right? And log n by n is a quantity that goes to 0 as n tends to infinity, but it goes to 0 slower than any polynomial in n, right? It's slower than n to the, say, minus 0.001. Okay. So we have this upper bound and we have this lower bound. The question is, if I'm only interested in the first order, right, just the rate itself, then as n tends to infinity, the optimal rate of compression is entropy, h of x. Right? So that's the first order term. Suppose I'm also interested in lower order terms. So essentially what I can do is the optimal rate of compression is h of x plus some function of n, which goes to 0 as n tends to infinity. And one can show that this g of n, at least you can again write g of n as a sum of lower order terms. And it turns out that the most dominant lower order term is something that decays to 0 as 1 over square root of n. And the corresponding constant that comes with it is the variance of what is called the var entropy. It can be interpreted as the variance of log 1 over x. Of log 1 over p of x. All right, that's the only point I was trying to make, nothing too deep. Any questions? Okay. So we discussed entropy and properties of entropy, and we've also seen KL divergence, which is sum over all x, p of x log p of x by q of x. We saw some properties of the KL divergence. In particular, the KL divergence is always non-negative. And the KL divergence is always convex in the pair PQ. Right? All of these were essentially consequences of Jensen's inequality. We also defined the mutual information between a pair of random variables, or in other words, the mutual information for a given joint distribution Pxy. So this was the KL divergence between Pxy and Pxpy. If we interpret the KL divergence as a measure of distance between two distributions, it's not a true distance because it is not symmetric. But if we take it to be a measure of, let's say, similarity or dissimilarity between two distributions, then the mutual information is essentially a measure of how close a given joint distribution is to being independent. So the KL divergence is 0 only if P of x is equal to Q of x, and the mutual information is equal to 0 if and only if the joint distribution consists of independent random variables. So the mutual information is always non-negative and equal to 0 if and only if x and y are independent of each other. All right. We could also write the mutual information as h of x minus h of x given y, or h of y minus h of y given x. Right? Along the same lines, just as we defined entropy and conditional entropy, we can also define the conditional mutual information, which is I, X, Y, Z, or to be more precise, I, X, Y given Z. So this is the conditional mutual information between X and Y given the random variable Z, and this is just h of X given Z minus h of X given Y and Z, which is the same as h of Y given Z minus h of Y given X and Z. Okay, it's just a definition at this point. But this leads us to a natural chain rule for mutual information, similar to the chain rule that we had for entropy. So if I have three random variables X, Y, and Z, the mutual information between X and the pair Y comma Z, this can be written as the mutual information between X and Y plus the mutual information between X and Z given Y. Likewise, it's equal to the mutual information between X and Z plus the mutual information between X and Y given Z. This just follows from the chain rules of entropy that we have seen previously. So the mutual information between X and YZ this is equal to h of YZ minus h of YZ given X, just by definition. Now this is equal to h of Y plus h of Z given Y by the chain rule of entropy minus h of Y given X minus h of Z given Yx. So I've applied the chain rule of entropy twice to each of those two quantities. Right? So I have h of Y minus h of Y given X plus h of Z given Y minus h of Z given Yx. All I've done is just rearrange the terms, nothing else. So the first term is what? It's just the mutual information between X and Y. And what is the second term? It's the mutual information between X and Z given Y. Right? Or Z and X given Y. So just the chain rule of entropy can have a lot of very nice consequences. Any questions? So maybe let's, I'll introduce another inequality at this point, or maybe let me do it a little differently. So what I'll do now is maybe spend some time solving a few problems, just so that we get completely comfortable with some of the ideas that we've seen before. Okay, so let's start with something very basic. Try to compute the mutual information for a bunch of particular distributions. And we'll see that these will be important for us later on in the course, particularly when I'm talking about channel coding. All right. So let's consider joint distribution, which is the following. So I have two random variables, x and y. You can treat this x and y as the input and output of a particular noisy channel. Okay. So the input x is Bernoulli P, and the output y is obtained by flipping x with some probability q and leaving it as it is with some probability 1 minus q. All right. So y is equal to x with probability q, and it's equal to, it's equal to x bar, that is the complement of x with probability q, and it's equal to x with probability 1 minus q. Okay, I'll represent this using the following channel transition diagram. So there are two different values that x can take and two different values that y can take, 0 and 1. So if x is equal to 0, then y is equal to 0 with probability 1 minus q. If x is equal to 1, then y is equal to 1 with probability 1 minus q, and they get flipped with probability q. Okay. So this is what is called the binary symmetric channel. With crossover probability q. When I say a channel, it's nothing but a conditional distribution py given x. That's all it is, nothing more. Okay, it's some py given x. So the moment it is some, I have an input distribution and a conditional distribution that fully specifies the joint distribution between x and y. Okay. Now my goal is to find the mutual information between x and y. So how would you go about computing this? What do I need? What are different ways of computing this? I'm sorry? Okay, there are two different ways I can go about this. I can write ixy as h of x minus h of x given y, or h of y and minus h of y given x. Both are equally valid, nothing wrong with either of them. Which one would you prefer? Okay, h of y minus h of y given x, that will be a little bit easier, right? Mainly because we get h of y given x almost for free. It's very easy to compute, but you also need to compute h of y, right, which requires a little bit of effort, not too complicated. All right. So ixy is equal to h of y minus h of y given x. So let's try to compute these. For this, let's do the easy part, which is h of y given x. Um, you know the problem. Again, there's no unique way of doing this, but this particular approach will sometimes be helpful for more general cases. All right. In this case, I agree because I can write what the joint probabilities are, and effectively I can also find the marginals. But doing it with the Kehl divergence will essentially be not much easier than doing this. The other advantage of going through this approach is, as a byproduct, I'm also calculating the entropies of x, y, and y given x. That's all. Okay. All right. So how do you compute h of y given x? If I give you an arbitrary channel, then h of y given x is very easy to compute because it is equal to sum over all possible x, h of y given x equal to little x times px of x. Okay. But what is, if I fix a particular little x, so x equal to 0 or x equal to 1, what is h of y given x equal to 0? So I fix x equal to 0 and I'm only looking at these two probabilities. So what is y given x equal to 0? It is Bernoulli Q, right? Given x equal to 1, it is Bernoulli 1 minus q, right? So this is equal to x equal to, I can write this as h2 of q times px of 0 plus h2 of 1 minus q times px of 1. Right. But we know that Bernoulli q, so what is Bernoulli 1 minus q in terms of Bernoulli q? Yeah? Bernoulli 1 minus q is equal to Bernoulli q, right? Because what is Bernoulli 1 or Bernoulli q or Bernoulli 1 minus q? It is the entropy corresponding to or the binary entropy of q and binary entropy of 1 minus q are the entropies corresponding to q comma 1 minus q and 1 minus q comma q. But we know that entropy is the same even if you relabel the alphabet. Right. So h2 of q is equal to h2 of 1 minus q. So this is h2 of q times px of 0 plus h2 of q times px of 1, which is just the binary entropy of q. So it's very easy. It has a nice simple form. Right. Now I need to compute the entropy of y. For this, I need to compute the marginal corresponding to y. So what is the distribution of y? It's a Bernoulli random variable, but I need to find the parameter. So what is the probability that y is equal to 1? Right, or let me correct. So I know that x is Bernoulli p. right? So can you tell me in terms of P? It is 1 minus Q times P plus 1 minus P times Q. Right? Is everybody okay with this? It's just probability that y is equal to 1 is the probability that x is equal to 1 and y is also equal to 1 plus the probability that x is equal to 0 and y is equal to 1. So this is, so the entropy of y is simply the binary entropy of 1 minus q times p plus 1 minus p times q. Is this okay? Fine. So the mutual information between x and y is equal to the entropy of y minus the entropy of y given x, which is the binary entropy of 1 minus q times p plus 1 minus p times q minus the binary entropy of q. Now, the nice thing about this binary symmetric channel is that there are different interpretations, different ways of looking at the binary symmetric channel. One can view this as an additive channel, but this addition is not over the reals, but rather over the binary field, or it's the XOR. So you have X and Y can be written as X XOR Z. Where X is Bernoulli P and Z is Bernoulli Q. Right. That basically amounts to flipping y with probability q and leaving y as it is with probability 1 minus q. Okay. So it's a very useful interpretation to keep in mind. But the nice feature about this is that what is entropy of y given x? In fact, it can be any such additive channel, not necessarily just the binary symmetric channel. And it doesn't matter what the distribution of z is. So let's say that so suppose that y is equal to x plus z, where this plus can be a very general form of addition operation. It could be addition over the reals, it could be an addition over binary sequences, that is over the binary field, or something more general. Alright, so what is h of y given x? I claim that h of y given x, irrespective of the distributions of x and y. Okay, another assumption is that x and z are pairwise independent. Okay, that's another assumption I will make. So this models a general family of additive noise channels. Okay, so you can think of x as the signal, z as some form of noise, and you want to know what is the amount of uncertainty in y, given that somebody tells you what x is. So intuitively, this should be equal to the entropy of Z, right? Because if I tell you X, then the residual uncertainty in Y should be just the uncertainty that is coming because of Z. Because X and Z are independent of each other. That's something very important to keep in mind. X and Z are independent. So in this case, intuitively, this should be equal to h of Z. That would be our first guess. Right? Intuition is not enough. We want to prove this. So let's try to use the properties of entropy to prove this particular statement. So I have h of y given x. Our favorite trick will be what we did in the previous class. We introduce the new random variable z and then try to get this particular quantity. So I somehow want z coming into the picture. So let me take h of y z given x. Okay, I'll start with this quantity, h of the entropy of y and z given x. And we'll use the chain rule in two different ways. So this is equal to h of y given x plus h of z given y and x, and it's also equal to h of z given x plus h of y given z and x. Is this okay? Nothing complicated. What can you say about h of z given y x? It's 0 because if I give you y and x, then you know that z is equal to y minus x. So the entropy should be equal to 0. It's a deterministic function. Z is a deterministic function of y and x. Similarly, what is h of y given zx? That's also equal to 0, right? Because y is equal to x plus z. So both these quantities are 0, which means that h of y given x is equal to h of z given x. But what do I know about z and x? They're independent of each other. So what is h of z given x equal to? It's equal to h of z, right? So h of y given x is equal to h of z, exactly as your intuition suggested. So that's a particularly useful property to know, because later on, when the context of channel coding, when we're trying to find, let's say, the mutual information between x and y, for a system where y is equal to x plus z, h of y given x we know is exactly equal to h of z. So it's very easy to compute h of y given x. All right. This also tells us something, that is, suppose I have such an additive noise channel where z is independent of x. If I look at the mutual information, right, the mutual information between x and y, this is equal to h of y minus h of y given x, or h of y minus h of z, right? But I know that the mutual information is always non-negative, right? Because this means that h of y is always greater than or equal to h of z. And likewise, h of y is always greater than or equal to h of x. You can prove using an identical fashion. just by computing the mutual information between x and z. Right? So this basically tells you that if I take two random variables, independent random variables, and add them together, then the entropy can only increase. It can't decrease. All right? So as a consequence, let's look at the following case where I take a sequence of random variables x1, x2, x3 and so on, where xi is equal to xi minus 1 XOR zi, where zi is some Bernoulli P random variable and zi is independent of zj for all I not equal to j. So all of the zi's are independent of each other. I take a sequence of Bernoulli P random variables essentially, and then I form the cumulative sums. Alright, so x1 is equal to z1. I'm assuming that x0 is just 0. Alright, so x1 is equal to z1, x2 is equal to z1 XOR z2, x3 is equal to z1 XOR z2 XOR z3 and so on. Okay, where all of these zi's are independent and identically distributed Bernoulli P random variables. What can I say about the distribution of xi eventually? Correct, but can I say something even stronger? What would you guess this would be? What distribution do you think this would converge to? That's the right guess. It's going to eventually go to the uniform distribution. Right? That's again, you can prove that. You can try to find the distribution. You know that P. So suppose that xi is Bernoulli. Suppose that xi is Bernoulli, let's say pi. All right. Then xi plus 1. Xi plus 1 is equal to this Bernoulli pi random variable XOR a Bernoulli P random variable. All right. So this would be Bernoulli pi times 1 minus p plus 1 minus pi times p. Alright, so this basically comes from the fact that the probability that xi plus 1 is equal to 1 is equal to the probability that xi is equal to 1 and zi is equal to 0 plus the probability that xi is equal to 0 times the probability that zi is equal to 1. Right. So that's the distribution of xi plus 1. But what exactly is this quantity? This can be interpreted as a convex combination of pi and 1 minus pi. Right? So I have at any stage I, if I take this interval from 0 to 1, suppose that this is my pi. For now, I'll just assume that pi is less than half, but the same thing holds true even if pi is greater than half. You just flip pi and 1 minus pi. So this is 1 minus pi. For any p strictly between 0 and 1, pi times 1 minus p plus 1 minus pi times p is a convex combination of these two, and it will lie strictly between pi and 1 minus pi. So my pi plus 1 is going to lie somewhere strictly between pi and 1 minus pi. Right, so maybe this is my pi plus 1 and this is 1 minus pi plus 1. So as I increases, pi and 1 minus pi get closer and closer to each other. It's symmetric, so eventually it must go to half. All right. So this is a case where I'm using something a little stronger than just this. H of y is strictly greater than h of z. All right. So the entropy is strictly increasing, and if it keeps increasing, the maximum value it can achieve is 1 for the binary case. So the maximum value, as n tends to infinity, the h of xn will tend to 1. Any questions? Okay. Let's see another example. We'll revisit the example later on, but it's an interesting application of data compression and entropy to a problem that is not directly data compression. Okay. We'll start with the following simple puzzle. All right. Suppose that I give you n balls. All right. Let's say I give you 8 balls. You may have heard of this example before. You are given 8 balls which look identical to each other, but one ball is heavier than the remaining balls. Okay. And your goal is to find out which ball is heavier using pairwise comparisons. You're given a scale, a balance. All right, so you're given a balance, and you can keep any number of balls on either side, and the balance is only going to tell you whether the left side is heavier or the right side is heavier. That's the only information that you get from this particular balance. All right, and the goal now is to find out which ball is heavier. So what would be your strategy? Correct. So the standard answer to this is you divide the 8 balls into 2 sets of 4 balls each, and then so you divide into 4 plus 4. Now given you can find out which set of balls is heavier than the other, and now you take one set of 4, the set of 4 balls which is heavier. This means that this set has the heavier ball, and now among these 4 you divide them into 2 plus 2. Maybe this side is heavier than the left side is heavier than the right side. So you take the left side and then again divide this into 2 plus 2. Find out which one is heavier, and suppose that this side is heavier, then you again split this into 1 plus 1, and now you have the heavier ball. All right. So that's a rather general framework. That's an easier, a simple way of doing things. It works for this case. All right. But how do you know that's a minimum number of trials that you need? Is it at all possible to do it? So how many weighings do I need in this case? 3. All right. But how do I prove that 3 is the optimum number? Can you show provably that you cannot do it using fewer than 3 weighings? Right. So this is where information theory can help. Now, let's try to view this in a different way. Okay. I have an experiment. You are free to design any experiment you want in such a way, right? All you get to see is observe whether the left side was heavier or the right side was heavier. Okay, we can take this in general, any number of weighings. Now, each weighing gives me some particular output, either left side heavier or right side heavier. Let's say that left side heavier is 0, right side heavier is 1. Okay, so I have W1, W2, W3 and so on. Suppose I can do it using by weighing things k times. I design this experiment where I do k weighings and I get the output. Okay, and then I'm able to declare which of the balls was heavier. Okay, and each Wi is either 0 or 1. This is a very general framework. It is not just weighing, but you can take any such measurement, so to speak. You design an experiment where you take individual measurements. Each measurement can potentially depend on the output of the previous measurement. That's okay. But each measurement gives you a 1-bit output, either left or right, or 0 or 1, or something else. Okay, so to put it in information theoretic terms, each measurement gives me 1 bit of information. All right, great. So now I'm making k measurements. How many bits of, what is the maximum number of bits of information I can possibly get using 8 bits of, using 8 measurements or k measurements? K bits, right? I can't get any more than k bits of information in k measurements. The total information I get could potentially be lower than k bits, but it in no way can exceed k bits. So, and how much, so the amount of information that I get is basically k bits. So this is the total uncertainty that these measurements can resolve. Okay. Now, how much uncertainty is there in the source? Right. In this case, there were 8 balls, out of which 1 ball is heavier than the rest. So, and I have no prior information on which ball is heavier. They're all identical to each other, right? Since all of the balls are identical to each other, each configuration, if I sort of order the balls, ball number 1, 2, 3, 4, 5, 6, 7, 8, each ball is equally likely to be heavier or identical to the rest, right? So how many possible configurations are there? Equally likely configurations are there. For the, if I take a configuration to be normal, heavy, normal, 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 and so on. So normal means it's not the heavier ball, and H means it is the heavier ball. Okay, and I have some ordering. Right? How many configurations are there? 8 configurations, right? So there are 8 possible configurations. So how much uncertainty is present in the input configuration? There are 8 equally likely outcomes. So log of 8, so 3 bits, right? So I need, so h of x is basically 3 bits, right? Which means that my measurements should give me at least 3 bits of information. So in no way can I do these measurements using any fewer than 3 measurements. Right? If I have binary measurements, then I can't measure them using, I can't recover the true configuration using any fewer than 3 measurements, any fewer than 3 measurements. Right? Another way of interpreting this is the following, right? You have the source X and your goal is to design this particular series of experiments or series of measurements which can be interpreted as a sequence of yes or no questions, right? In this case, yes or no questions could be, is the left side heavier than the right side? Okay, and that gives you W1, W2, and you make a sequence of measurements. And using these measurements, your goal is to say what X is, and you want it exactly. So this can be posed in some sense as a compression problem, because you want the fewest number of measurements that amounts to designing a source code with the smallest length. There's a little bit of a nuance over here. In this case, I was interested in the maximum number of measurements, whereas the source coding theory tells you what is the minimum expected number of measurements. But if the minimum expected number of measurements is something, then the maximum number of measurements can only be higher than this. All right. So this theory of source coding can help you give useful lower bounds on problems such as this. And in many cases also give you algorithms to find out if you have a good compression algorithm. It also tells you what is a good sequence of measurements such that the average number of measurements is minimized. All right. Maybe a better example than this, there's a little bit of a subtlety over here in that in this particular example, when I'm doing measurements, it's not exactly binary, because in principle I can also allow both sides to be equal. Right. So in fact, what I get per measurement is not 1 bit, but a little more than 1 bit, because there are three possible outcomes. Left side is heavier, right side is heavier, and they're both equally balanced. And
how can they both be equally balanced if you know that one is heavy?
but it's a measurement, right? For whatever reason, I could say that I could put, let's say, 2 normal sized balls on either side. Let's take another extreme example. Suppose there are 3 balls, all right, out of which 1 ball is heavier than the rest. Now what can I do? I can just pick 2 arbitrary balls, place them on either side. If the left side is heavier, then I know that that ball is heavier. If the right side is heavier, then I know the right ball is heavier. If they're both equally balanced, then it means that the one I didn't pick is heavier. All right. So strictly speaking, these measurements are not binary but ternary. But that's okay, because it simply means that the total entropy in the measurements is not exactly k bits, but rather this is at most k log 3 to the base 2. In every measurement, I'm getting log 3 to base 2 number of bits of information. All right. And this has a lot of applications. One very popular application is this problem of group testing. The basic group testing problem is the following. You have a bunch of items, or let's say you have a bunch of people. You can take the example of, let's say, testing whether a particular person has been infected with a disease or not. For example, COVID. All right. So you have n people, out of which, so n people, out of which k are infected, but you don't know which of the k are infected. Now what can you do? The only way to find if whether a person is infected or not is to conduct a blood test. All right, and to conduct a blood test, the output of the blood test is either positive or negative. That this blood test has samples of the infection or it does not have samples of the infection. So the number of bits of information that you get for a particular blood test, let's suppose that it is either positive or negative. So just one bit of information. And your goal is to find those n people, find those k infected people using the minimum number of measurements or minimum number of tests. Back when we had COVID, during the pandemic, the problem was you didn't have enough kits, right? So one naive way is to test each person and find out which person was infected. But if you have some prior information, that is not too many people are going to be infected, maybe 5 out of 100 people are infected, then it really doesn't make sense to test all the 100 people to find those 5 people. There is potentially a better way of doing this. And one way of doing this is to pool people together. Okay? What you can do is take blood sample from a bunch of people, pool them together, and use a single test. What the test will indicate is whether at least one person from this sample is infected or not. All right? So potentially, as an example, you have 100 people, you split them into 2 groups, all right, of 50 and 50. And you test, you pool the samples corresponding to the first 50 people, and you make a test. You use, let's say, one kit to test this sample. If it returns a negative, if it returns a positive, then it means that there's at least one infected person from this set of 50 people. But if it returns a negative, then it means that you don't need to test anyone from this set of 50 people at all, right? Which can be very advantageous. You've just eliminated 50 people with just one test, right? So there's a way of cleverly grouping together. In the context of group testing, this is called pooling. So you can pool people together such that you can, in order to find out which people are infected. So now, suppose that I have this particular mechanism, this way of pooling tests together. What is the minimum number of tests that I have to perform? The minimum number of blood tests that are required. I don't need to know the exact value. It's okay if I don't come up with the algorithm, but for now, can I give a lower bound? What is the minimum number of tests? It has to be greater than or equal to this amount. How many possible configurations are there? There are n choose k possible configurations, right? There are n people out of which k are infected. So the total number of configurations is n choose k. So what is the minimum number of bits of information I should get in order to find out which of these configurations is the true configuration? It's log base 2 of n choose k. So I need log n choose k to base 2 number of bits, at least this particular quantity. I may or may not be able to do it using this many, but I definitely cannot do it using fewer than log n choose k tests. All right. So this gives an automatic lower bound. So this is the minimum number of tests I need to do, or the minimum number of tests I need to do has to be at least log n choose k. Now this was a rather simple application, but still it tells you that this particular approach is very useful and it goes far beyond just simple data compression. Right? The same ideas could be extended to this whole host of other problems. Right. Any questions? Questions? All right, so I think it's a good time